Hello, in this video we're going to continue on with our discussion about the fundamental theorem of algebra. As we said in the past several videos, the fundamental theorem of algebra describes the relationship between the degree of the polynomial and the degree and the total amount of zeros of that polynomial. And in the last video we discussed irrational zeros, and the one prior we discussed real zeros, and now we're going to discuss imaginary zeros. So we're going to talk about imaginary zeros. And imaginary zeros sound a little awkward, and at this point it's only important that we know how to calculate them and then how to derive, we're eventually going to learn how to derive the polynomial based off those imaginary zeros. So can we really graph them on the real plane, on an xy plane? No. But if you continue on with your math education, you're going to realize that you can graph them on an imaginary plane. But for right now, we just want to be able to calculate them and understand them. So let's go ahead and look at an example. F of x equals to, let's say, x squared plus 6x plus a value of 10. Actually, let's say minus 6x. Yeah, let's say minus 6x. Yeah, let's say minus 6x. There we go. Let's say, so minus 6x, that's a really bad minus. There we go. So minus 6x will look like that. And now let's say we want to determine the solutions. Let's say we want to determine the solutions of this polynomial, or where the graph crosses the x-axis, and the solutions are also known as the roots, which are known as the x-intercepts. Those are all synonymous terms, so we can go ahead and use our quadratic formula. So I'll say it correctly this time. It is the quadratic formula, and our quadratic formula is going to be x equals to negative b plus or minus the square root of b squared minus 4ac all over a value of 2a. So that's going to be my quadratic formula. Notice here my coefficients are going to be my a, b, and c values. So my a is the coefficient in front of the x squared. My b is the coefficient in front of the x, and here it's a negative 6. And my c is the coefficient, is the constant term. So my c is the constant value of 10. So my c is the constant value of 10. So now all we're going to do is just plug in. So I'm going to plug in. So x will equal to negative b, but b is negative 6. So I have two negatives there, plus or minus the square root of b squared, and that's going to be negative 6 quantity squared minus 4 times a, which is 1, times c, which is 10. So I got all those terms plugging in directly from here. So b squared is the negative 6, and the a is the 1, and that's going to be corresponding to this value, and the c is the 10, which corresponds to this c, and that's the 10. But we still yet have to divide this entire equation by a value of 2 times a, but a is a value of 1. So all we're doing is plugging directly in to that formula. Whoops. Simplifying this, we're going to have x equals to negative 6 gives you a positive because we're multiplying the two negatives together. So we're going to get a positive 6 plus or minus the square root. Negative 36 quantity squared gives you a positive 36. Minus 4 times 1 times 10 gives you minus 40 all over a value of 2. And notice here we're going to get 6 plus or minus the square root. 36 minus 40 gives me a negative 4. A negative 4 all over a value of 2. And if I want to simplify that further, I'm going to have 6 plus or minus square root of negative 4. Going back to our imaginary solution workshop is going to be a value of 2 times I, because I is equal to the square root of negative 1. Still all over 2. I'm going to factor out a 2 in the numerator. So I'm going to have 3 plus or minus I all over 2. And now my 2's cancel, so I get 3 plus or minus I. 3 plus or minus I. So in essence, this quadratic has a solution that exists at 3 plus I on the imaginary plane. And then it also has a solution that exists on 3 minus I. So one thing that we want to note is that these two values, that's a horrible print bracket. So these two values are called complex conjugates. They are complex conjugates because the coefficient, the sign of the coefficient in front of the I changes. So one's a positive, the other one's a negative. So notice with our quadratic formula, we have that plus or minus. We have this plus or minus that exists there. So we're going to get imaginary values when this portion, b squared minus 4ac, when the b squared minus 4ac is going to be less than 0. Is going to be less than 0. We're going to get imaginary values because that makes it negative, and the square root of a negative value is always going to be imaginary. So what we can characterize from this is that if a plus bi is a 0 of a polynomial, then its conjugate pair, a minus bi, must also be a 0. So, for example, if 2 plus 3i is a 0, then we also know that 2 minus 3i must also be a 0. If negative 2i plus 4 is a 0, then positive 2i plus 4 would be a 0. Notice here we're just changing the coefficient sign. So the negative 2 becomes positive. The positive 3 becomes a negative. So we know that they exist in conjugate pairs. And they're called complex conjugate pairs because they are complex. They have a real portion and imaginary portion. If negative 5i is a 0, then we know that positive 5i is a 0 because this is a circumstance where we have a plus bi, but our a is equal to 0. So that makes this go to 0, so we just get bi. So the complex conjugate of bi is going to be just negative bi. So each one of those are going to be zeros that must occur in pairs. One cannot exist without the other. Very similarly, how do we saw that same occurrence with irrational zeros? When we saw examples like 3 minus root 2 is a 0, then we know that 3 plus root 2 must also be a 0. So complex values and irrational values must occur in conjugate pairs.